All right, it's 4 o'clock. I hope everybody can hear me. If we can't, let me know. Hi, everybody. I'm Nick, for those of you who don't know me. So I hope you're all doing well and staying safe. So again, for the next 2 hours, I'll be answering your questions. I'm going to share my screen now to kind of have a whiteboard so we can all look together. But kind of what's going to happen here is very similar to last time. If you have any questions, just unmute yourself and ask it. If you have any just questions that you don't want to be anonymous or something, if you want to be anonymous or something, you feel free to just put it in the chat. If you have anything that you want me to just talk about just as I'm doing a problem too, or want any clarification, I'd be happy to do that. I have all of the problems from the couple of worksheets that were handed out from DJ's and mine that I handed out, including the solutions too, so we can go over that. I can talk about just concepts, just in general. I can really do whatever you guys want me to kind of do, other than tell you what's on the exam, because I have no idea. Without further ado, I will, does anybody have any questions you want to start off with here? Feel free to, anybody that wants to start off with a question, feel free to mute yourself and go for it.
Hey Nick, I was wondering if you can give an overview of the geometric interpretations of the exercises.
So do you mean what do the triple integrals and double integrals mean, just in general?
Yeah, just how we have questions even on our worksheets, what is the geometric interpretation of it may be in spherical coordinates dv in spherical,
sure.
Those kind of questions.
Sure, I can kind of discuss that. So I guess the first thing we want to just know is kind of what is everything. And this is kind of building from just the basic idea here of something like this, even back in Calc 1 when we were kind of dealing with this. So what does this actually physically mean? If I asked you this, and what would this actually physically mean, right? What is this actually saying? This is saying that, I have my function f of xy. I have something like this here, and I am between 1 and I'm between 2 here. And this is actually telling me I'm actually trying to find the area under the curve between f of x and between the x-axis. So if I'm trying to understand this, this is just kind of talk about the area. Now, this can also be negative, right? So for instance, if I had a function, something like this instead, right? In this case, my area under the curve would be negative. So we kind of call this kind of like a net area, which kind of discusses how much is above and below the x or x-axis. Now we can again just keep interpreting this, going forward here in the same exact way. If I just have a two-dimensional integral here, and now I want to understand what this is. Well, it is the same exact idea. I now just have a two-dimensional domain. So I have this two-dimensional domain now, maybe something like this here. And at every single point, we can kind of consider, this f of x as kind of like a height, right? In kind of thinking about the height here is really like how far away I am from the x-axis. But in general, I can think about the f of xy as kind of a height, but it could be below and could be above. So what is this basically saying, right? This is saying that I'm taking every single point in my domain. I'll let this domain have a little bit of chicken pox. Every single part of that domain, I'm going to find the height. I'm going to find what that function value is going to be. And I'm going to add all those contributions up. They could be below the axis, they could be above the axis, and so on. And they could be below the xy plane, above the xy plane. And so because of this, we kind of consider this a net area, net volume, I'm calling it. Because we kind of have a kind of a base, which is this d, kind of this domain d. And then we also have like a height. So it's base times height in some manner. Now, what do we do with this dA, right? Why do we have this dA here? Well, this dA is kind of a differential. In this case, this is also the differential here. We only have dx because we're in one dimension. So we only have one kind of variable to deal with. This dA though, if I'm in Cartesian coordinates, we have dy and dx. And now think about why this makes sense, right? This is an area differential. So I need to kind of have a length squared. You want to think about what the dimensions are kind of. So x is a length and y is a length in some way, right? If x is a length and y is a length, then based off of that, I can get length squared. Now, if I wanted to convert this to polar coordinates, by kind of thinking about what this means, what I would have to do is I would have to let x be r cosine of theta. I would have to let y be r sine of theta. And then what I'd have to do is I have to kind of change this differential. I would have this dA. Now, what's this dA? Well, now I'm only dependent on r and theta. And so if I think about dA now, and I want to go to dr d theta, well, does the dimensions make sense? And you might say to yourself, they really don't, because the length, I have length squared here, and then this is really a length, but this isn't. The angle here, the theta here, is not really it's not a length scale. It's an angle. It doesn't really have that many dimensions. It doesn't have dimensions at all. So in order to make these kind of similar, you can kind of find that the area, I have to add this r to kind of make this length squared kind of make sense. And you can kind of also think about that the area in a polar rectangle can actually be calculated by this quantity. I'm not going to go through that whole calculation. It's a really kind of just a complicated derivation, but you can kind of go through it using the sector formula of s equals r theta, kind of going from there. Now, that's why we always have to add this kind of this r dr d theta when we convert to polar coordinates. And then similarly, you can continue going up to triple integrals in that same exact way. Now, this is a little bit of a weirder interpretation here, because there's so many different types of interpretations we can have in this kind of this type of an integral. But the best way I like to think about it, in my opinion, if I have this e here, you kind of imagine that this is like some object, like a water bottle, right? And this f of x, y, z, let's assume that this is positive for right now, but we don't have to. Kind of imagine that that's kind of the density at every single point on the surface and inside the surface too. So kind of, what if I told you at every single point on here, I gave you a density of what it is? Because you can see the material here, up here, and this part of the water bottle is different than this material, and kind of so on. And what I can do instead is, if this is this, the integral over all of this will actually get me the mass of the object. And because of this, we can kind of consider this. There's a lot of weird interpretations of this here, but the biggest one I would suggest is probably like a net mass. However, the best interpretation is usually when f of x, y, z is equal to 1. And we usually consider this is actually the volume of E. And you can kind of see this in a certain way, because if I just make a 1 here, the first integral is going to be very, very quick, right? It's just going to be the top bound minus the lower bound. So you can kind of think about this as a height and then convert it back to a second two-dimensional integral. So this is actually considered the volume integral. If I just have, just E, and this will be a positive value. Now, how do I convert to different coordinate systems here, and how would I go about doing that? And kind of what the interpretation is here. Well, the first thing is really cylindrical coordinates. If anybody has any questions, if they want to hop in here and just or message me or something like that to talk about, I'd be happy to. But I'm just going to talk about cylindrical coordinates and kind of understand how we get to changing it there. I'd be happy to stop at any point here and kind of discuss anything. But I just want to get this out of the way. This is a good question to start off with. So if I want to go to cylindrical coordinates, what are cylindrical coordinates actually saying? I always like to think about this, on a cylinder, right? I have kind of my water bottle. This is a really good prop just in general. So what does a cylinder tell me? If I want to talk about all the objects on a cylinder, how do I do that? Right, so if I'm up here, how do I have to tell you to be up there? Well, I have to kind of tell you the z height still makes sense. So if I'm a point here, a z height still makes sense here. Usually we would do then x and y if I'm thinking about Cartesian coordinates. But what I can do instead is say, okay, well, I know this is going to be circular on the xy plane. So if it's going to be circular on the xy plane, I might as well use polar coordinates to define by an x and y. That's what kind of happens. So what I do instead is I say, okay, I'm going to tell you the r theta component. I'm going to tell you the polar coordinate for my xy, whatever I project onto the xy plane. And I'm going to give you that z coordinate. So you can define every point r, theta, and z. And based off of this, right, what I can then start to do is, very basically, if I want to convert, you have x equals r cosine of theta and y equals r sine of theta. Because in the same exact way, this is just an extension of a polar coordinate, just in multiple dimensions, more dimensions. And z is equal to z. This is the best equality you will ever write. And now based off of this, right, based off of this, how would I convert an integral to that? Right, so if I have something like this here, and I have f of x, y, z, let's assume I have this whole thing, right? What is this dv now? Usually we had this as dx, dy, dz in the past, right? We would have three, we have a length cubed now. I'm thinking about a differential in 3 dimensions. So I need 3 things to be multiplied. I get length times width times height. That's why we get the dx, dy, dz. Now I have something that's a little bit cylindrical, but the z is not changing, right? So if I think about this now, if I want to maybe convert this to dz, dr, d theta, right? Well, think about it this way. This is again a length, this is again a length, and this is again nothing. But the only thing I changed was the r and theta. So I really shouldn't add a z component at all. I should be adding, as we had the last time, an r. Since I changed it to polar coordinates last time with r and theta, all I've done here is really just change the x and y to polar coordinates. So therefore, I want to change to cylindrical coordinates. I want to add this r. And because of that, right, I can now exchange this. What I do is every single place I see this, I replace with r cosine theta, r sine of theta, and z. And I multiply it by r, dz, dr, d theta. Usually in cylindrical coordinates, we usually go in this exact order because sometimes z is dependent on r and theta. R is almost always dependent on either constants or sometimes it's dependent on theta, and theta will always be constant. If it went the other way, that would be horrifying, and we won't have problems with that here. There are problems like that, but they're much higher levels. And so this is how you would convert that. And again, here, what this is asking, just saying is, why would we convert this to cylindrical coordinates, right? Why would we do that? Well, if we notice something on the xy plane would be polar. We notice if I project the surface of the xy plane and it's polar, right, that gives us a really good interpretation. If it's a really nice z, right, if I can tell you where I'm entering and exiting the region from and then project it down, if I get a polar, that's not bad, because then I can kind of go back. And lastly here, the last one and the most interesting one always, I think, is the spherical coordinate question. So if I have spherical coordinates, I am a big space nerd. And one of the things I like to always think about is, if I was to tell you where a star is, how would I tell you where a star is, right? How would I tell you that? So how would I go about in telling you where a star is? So the first thing you kind of say is, okay, well, X, Y, and Z really wouldn't make sense. The Earth's not a cylinder, so that really wouldn't make sense either. Maybe a sphere, the idea of the sphere. So how would I think about that? Well, one way I could tell you is how far away is that object? Right? How far away is the object? And if I tell you how far away the object is, that would be rho. It's kind of the distance away. And what you can kind of see by using an extension of the Pythagorean theorem, in this case, is that you can find that x squared plus y squared plus z squared is equal to rho squared. Because you can kind of imagine, x squared plus y squared plus z squared is equal to 4, for instance, is a sphere of radius 2. So if I tell you that rho is equal to 2, those are all the points that are 2 away from the origin. And that would define a sphere. And so that's kind of how we would think about it that way. Now, the other thing I need to tell you is, okay, I tell you how far away I am. The next thing I would like to maybe say is, where do I have to face my telescope? Right? If I'm going in this way, where would I have to face my telescope to kind of make sure I aim in that direction? And that's kind of, the angle in the XY direction, right? That's the angle in the XY. So if I'm thinking about the angle in the XY direction, that again comes back to the polar angle. And so again, I could tell you here, I could tell you this polar angle again, and maybe tell you specifically, where do I have to face here? And maybe it's actually this polar angle right here. And lastly, so I've now told you how far away I am. I've told you which direction I need to face. The last thing I need to do is kind of angle the telescope either down or up, depending on where I am. And if I then think about, okay, where do I have to tell you to face in that direction? We can kind of say, okay, from the angle from the z-axis, this part up here, the angle from this z part, how far down do I have to go until I reach that part? Right, until I reach that angle that I'm at. And so this is called phi, we usually denote it as this angle right here. It also has a name in physics called the Azimuthal Angle. If you want to know that, that's okay, but that's not really something interesting, but that's how physics people sometimes use it. And what we're saying here is the angle from the top all the way down to down to here. So when I think about phi being 0 is strictly at the top, is straight up at the z-axis, and I go down like this. So this is kind of the idea. Now, where do all these things run? And it's really important to think about, what can these values be in the same exact way that we thought about for polar and cylindrical. So rho here has to strictly be positive. I have to have positive radii in the same way that r has to be positive. Now, theta runs exactly the same exact way. I have a full 360-degree turn here. So I would have my theta would be between 0 and 2 pi. And then think about it this way. What would phi have to be? Now, if I tell you phi equals 0 is up here, phi equals 0 is all the way at the top. And then I tell you phi, I go down to here, and that goes phi pi over 2. And then I would go down even farther to the negative z-axis, all the way down here. That would be phi equal to pi, phi equal to pi. Does it make sense for me to go backwards? Right? Does it make sense for me to keep going? And the answer is no, because if I go back this way, I can just change my theta direction and orient myself this way by keeping phi maybe at a more constant pace without going over pi. And so because of that, we actually find that phi will be between 0 and pi. So if I have a full circle, if I have a full sphere, my apologies, if I have a full sphere here, what I'm saying is that theta will have a full sweep of 0 to 2 pi, and phi will have a full thing of from 0 to pi. It will never be greater than pi, it will never be less than 0, at least in phi. So it does might be easier to think about it a certain way, but that's at least the basic gist of it. Now, how do I convert in a coordinate system? Right? How do I convert this to cylindrical? How do I convert this to spherical? Well, we need to know our x, y, and z things. The first thing you want to know is I always go really, really simply. You need rows everywhere. So I go row, row, row your boat. I always have everything there if you're having trouble remembering it. The next thing I would think about is the theta direction. Right? The theta direction acts very, very similarly, I hope you'd agree, to the polar angle. So you might say to yourself, oh, wouldn't it be nice if x had cosine and y had sine? Yeah, you're absolutely right. And z doesn't have that, because again, z is not dependent on theta. I can move in any direction. I shouldn't have any of that. The last thing you might worry about is how does this phi affect it? And the phi affects it in this following way. What I'm going to do, and this is actually a very important concept when trying to come up with spherical coordinates here. What we do is we project the point or in a surface, whatever you want to think about, onto either the xz or the yz plane. And the reason why is it allows us to really see something a little bit better. So if I project this point, we again see that this is going to be my phi here. Get that phi. Now, this is also phi down here, this little angle here. If I want to know my x, because this is x here and this is z, this x here is opposite of my phi. If my x is opposite, that would be related to, in SOHCAHTOA land, opposite over hypotenuse, that's going to be my sine. And so therefore, I should have a sine of phi attached to the x here. And similarly, if I project it onto the yz plane, I'm going to again get that sine as well, because it's going to be the opposite of there. And then if you note, the z coordinate here, this z coordinate is actually, adjacent to my phi. It's adjacent. And so therefore, because of that, I should expect that I should have a cosine of phi. And there are my transformations. And so this comes very, very nicely from geometry, which is good. And then so lastly here, the last thing I want to do is for this very long answer to this question, and I apologize for this very long answer, but I feel like it's a pretty important thing to kind of talk about, is how do I convert this, right? How do I go from, the dv here? What does the dv look like in this? Well, the dv comes, well, I need d rho, d theta, dc. I need these guys. And now let's think about dimension-wise. I need a length of a third. This is a length, this is an angle, so it's nothing, and this is an angle, so it's nothing. So I only have one length scale, right? I only have one length scale. And because of that, I need to add two more. I need to add length of the squared, right, to get my my volume to make sense. So I come here and I need to add this rho squared. There's no other length for me to add, so I can't do that. But I also need to add one extra element to it, and it's this sine of phi element. And the reason we need this is the same reason why we needed the r in the past, or why we needed to change different coordinates, how we change coordinate systems. What we're trying to find here is it's this triple Riemann sum almost. It is actually part of the triple Riemann sum. When I'm trying to figure out and approximating my integral, right, the ideal formal idea of the integrals, I basically make everything into little blocks. And then I add them all together as I make my block smaller and smaller and smaller. But here what I'm doing is I'm making spherical wedges. I have these little spherical wedges, like everything's on a sphere here. And because of that, you know, to make the dimensions make sense and to actually compute a volume of this mini sphere, I actually need to add this sine of phi. And so because of that, that's what this dv is kind of representing. And so if I convert this, right, if I convert this here, this integral of f of x, y, z, you know, dv here, I'm not going to write it all the way because it's a lot. But again, what you would do is you would plug in this guy, you know, this guy, and this guy into x, y, and z. Those parts that would be there. And then you would multiply by rho squared sine of phi every time. D rho, d theta, dc, something like that. And kind of just zooming out as a picture here, it's kind of getting back to your original question, Sanjita, and I apologize for kind of going over in a kind of a different way. The kind of geometric interpretations of all these two-dimensional, three-dimensional integrals all come back to either a volume or a mass of some sort, or maybe like some form of that. And to convert, and the ideas of the differentials here all stem from making sure that my dimensions make sense. Right? I need a volume, I need length to the third. I have an area, I need length squared. And by utilizing the fact that I'm trying to figure out how do I accurately compute a volume using my new coordinate system, that's why I need to change it to rho squared and sine of phi. That's why I need to change it to r when I multiply it, when I change it to cylindrical or polar, something like that. So that's at least the basic idea here. I hope that makes more sense to some people. And I don't know if I accurately answered your question, Sanjita, but that was kind of what I went for there. Does that make sense?
Yeah, that helps a lot. Thanks.
Great. Any other questions here?
Nick, I had a question about the
Yeah.
phi. So you say like it can't be greater than pi. So if you had like 3/4 of a sphere or something, would you do like 0 to negative pi over 2?
If you have 3/4 of a sphere?
Like if you had like the half a sphere, like from 0 to pi, and then you had another half on the other side.
Oh, so, interesting. Yeah, so that's all covered. So the thing is, that's all covered by the theta. Right, theta, I mean, if you're talking about, are you basically talking about 3/4 of a sphere? And I'm only taking off like that 1/4 here? Is that what you're describing there? So again, if I have that full phi sweep, that's all I'm caring about. That quarter that I'm missing is all dependent on the theta. Right? Okay. It would tell me I'm taking out this part here. Imagine like you're slicing a cake. I'm taking out just that part. That's a theta part. That's not a phi part. That's a theta. I'm like taking out that. So I should be more dependent on that. Phi only depends on really, you know, going from the z positive z axis all the way to the negative z. So if I have a full sphere, but I've just taken off like a theta component of it, if I just say I'm only taking 3/4 of it, I'm taking half of it in like the half direction, then I would think about it. If I cut it off, you know, in the xz plane or something like that, where I only have half a hemisphere, and I tell you that, you know, I would still have a full, you know, I would still have a full phi, but my theta would be different. To kind of cover. Does that make sense?
Yeah, it does. Thank you.
Okay, yeah, no problem. Oh, I was like, I have a ball. I can use it. So, great. Okay, where else shall I go? Any other questions that I can answer? I have all my.
So when is there going to be a scenario where phi isn't full?
Yeah.
So can we go over like an example of that?
Let me see if I have one. Well, I have several. Sorry, let me find one. Let me find one that makes sense. Yeah, so for instance, if I have something like this, so this is the problem. This is a problem from my worksheet that I handed out. That was from 15.8. Like this. So the problem is, yeah, I'm going to start with that. So it is the triple integral e to the x squared plus y squared plus z squared dv. I'm actually not going to go fully through this because it's a really long integral. I'm just going to set it up because that's the main part. So you have to imagine that, you know, for a 40-minute exam, they're not going to ask you to do really hard things, right? They're going to ask you to set up a lot of stuff, which is really the big goal, because mathematics can evaluate a lot of it. But the limits are really important. So where e here is the portion of the unit ball, x squared plus y squared plus z squared, is less than or equal to 1 in the first octant. Okay, so I am this ball just in the first octant, specifically a ball of radius 1. So let me try to draw this. And so I have a ball in the first octant. First octant is where x, y, and z are all positive. So I'm basically bounded by all the coordinate planes. I'm bounded by x equals 0, y equals 0, and z equals 0. Something like that. I tell people all the time I'm not very good at drawing, so I apologize, but this is at least the best I'll do. So this is the kind of sphere, just it's an eighth of this sphere, basically. I've just kind of chopped off this part and this part. I've just taken off part of like, yeah, something around there. I just chopped it off. Now, you can come up with this kind of bounds. I mean, you can evaluate these bounds really in any coordinate system. You can even do this in cylindrical. You can even do this in Cartesian. These would not be too bad in either, but to evaluate this integral, that would be pretty terrible in any other capacity. So I look at this integral just very basically, and I see that I have this x squared, y squared, z squared thing. And I see that that would be really nice if I could switch that to spherical coordinates, right? Because if I switch that to spherical coordinates, that exponential will become a rho squared, because x squared plus y squared plus z squared is rho squared. So that would help me out a lot instead of having e to the x squared plus y squared plus z squared. That's really a weird thing to integrate. So because of this, let's try to shift this to spherical coordinates. So the first thing we need to do is, I always think the easiest thing to do first is take out your rho. That's usually my opinion on that. Rho here is, again, you start off at the origin and you want to just see, you start off at the origin here, and I move out of the region. I just move out of the region as much as I can. I start at 0, 0, and I just go and enter the region and exit the region just with straight lines. Now, I hope you'd agree that this region, this 0, 0, 0 is in my region. I'm always entering from that point. So therefore, rho has to be bounded below at 0. It's kind of the same thing with r here. If that's in my region, right, I start off at 0. Where is it bounded above by? Well, one way you can kind of see this, up here, if I note x squared plus y squared plus z squared is less than or equal to 1. And I know that this is actually just rho squared is less than or equal to 1, which then means that rho has to be less than or equal to 1. And we see here that I'm always exiting the region from that sphere. And so therefore that sphere is equal to rho is equal to 1. So our rho would be just between 0 and 1. Now, where do we go for theta and c? I'm going to use different colors for theta and c. I will use blue. Theta here. So this is always the technique that you utilize. For theta, we project the surface onto the xy plane. Okay, so we project onto xy plane. And if I project this surface onto the xy plane, I hope you'd agree, because I'm in this first octave, I'm just going to have this quarter circle here. This quarter circle is just going to be there. It's just like that guy. And you can notice this if you didn't realize what the projection would be. If for instance you're like, I don't know what the projection would be, you can again just set z to be equal to 0 here, and I'll get that x squared plus y squared is less than or equal to 1, which is again just a circle of radius 1. But again, what's nice here is I don't care about the radius. I only care about the theta. That's all I care about. I care about nothing else. I'm just strictly trying to figure out what the polar angle is. Because of that, I see here that I'm on my x-axis and I'm going from 0 all the way to pi over 2. I'm going from 0 to pi over 2. So because of that, my theta will be from 0 to pi over 2. And lastly, I'm going to try to figure out my phi. Getting to your exact question here. Phi here, well, how do I figure out phi? Phi, you do either in one or two ways, whichever one you would like, or whichever one kind of makes sense to the problem, honestly. And what I mean by that, I'll kind of explain it. You project this surface now onto the YZ or XZ plane. Okay, you project it onto the XZ or YZ plane. So imagine you take this. I'm going to project this onto the YZ plane. I think it's a little bit easier, at least in this case, to kind of visualize. If you project this onto the YZ plane, I hope you'd agree it's just a smushed, it would just smush itself onto the YZ, and it would just be a quarter circle again. Right? It would just be a quarter circle. It'll be YZ. It will just be this guy. And now why is that again? Right? You could kind of think about, if I project onto the YZ plane, it's the same thing as saying X would be 0. So again, you would get X squared plus Z squared is equal to 1 as your circle. Now, how do I come up with my bounds for this? We again remind ourselves that going vertically up, this part right up here, this in the positive Z-axis, is my phi to be 0. Okay, so this is phi equal to 0. Now, you can either go clockwise or counterclockwise. It actually doesn't matter, but we have to kind of utilize our brain here to think about which one would be easier to do. Well, since I have nothing, if I go clockwise, counterclockwise, it wouldn't make sense. So I'm going to go clockwise here, just because that's where my region of integration actually is. I have to kind of go in that way. If you had symmetrical on both sides, it honestly does not matter. I usually like to just go in the clockwise direction. That's how I usually remember it. But you can do whatever you would like. If I had both sides, you can just go it that way. It will be the same answer. So here, we say that phi equal to 0. We would get that phi is equal to pi over 2 here, and phi is equal to pi. And so if I note here, I have my phi equal to 0 on top. I'm going down to phi was pi over 2, and there's my end of my region. My region is ending at this point. So because of that, we start off at phi equals 0. We end at phi equal to pi over 2. And because of that, my region would go from 0 to pi over 2. And then these are your bounds. We have rho from 0 to 1. And we figure this out by, just drawing lines out of my region. We have theta equals 0 to pi over 2, because that's my theta sweep. We project that onto the xy plane. And lastly here, if I want to figure out my xz, project onto my phi, I project onto the yz or xz plane. If I project onto the xz plane, I would get the exact same picture, actually, and I'll get the same exact answer. So because of this, we can now fix our integral here. The first thing you would always want to do when I fix this integral is you would want to exchange this entire function for spherical coordinates now. So the x here is rho times cosine of theta times sine of phi. This upper part up here can become a rho squared. And then we have to multiply it by our change in variables, which is rho squared dv. Rho squared times sine of theta, kind of paying the price. I think DJ kind of uses that term as well occasionally. I'm not too sure. I think DJ uses that term. I might be wrong, but I think he does. And that's kind of paying the price here in that way. And so because of that, what I now do is because this is all constant, and this is actually really cool, because these are all constants, this becomes actually a really nice integral. I can use my separable function theorem, and I can separate them individually. This is kind of a rectangle. I can utilize Fubini's theorem if I need to. A lot of things really come out nicely here. So I can go from 0 to 1, 0 to pi over 2, and 0 to pi over 2. This x now becomes rho times cosine of theta sine of phi. This becomes e to the rho squared. I'm going to zoom out really quickly. It becomes e to the rho squared. And we multiply this by our change in variables, rho squared sine of phi, d rho, d theta, d phi. And so this is our integral, and we can go evaluate this if you want to. We see that this is the separable function because I have a function that's a rho times a function of theta times a function of phi. And I can separate this and do this each one individually. We need a double angle identity here, and we're going to need actually integration by parts and u sub here too for the rho part. But regardless, this is at least how you set it up. And that's the most important part here, to kind of remind ourselves of this kind of process. For theta, project onto the xy plane. For phi, you project onto the yz or xz plane. And that's kind of how you figure this out. So does that answer your question, Camilla?
Yeah, it does. Thank you.
Great, no problem. Does anybody else have any questions about this specifically? Or anything you want me to touch on here, at least in this problem? Okay, so what else can I talk about then? What other questions can I answer?
Would you be willing to do a problem where you have to, like, you're given the bounds of the first one and then you have to show like the other 5 when you're given the triple integral?
Oh yeah, that's a good one. Let me see, do I have one of those? I think I do. Let me see. I think I do have one of those. Let me actually get my textbook. So those, a lot of times, you know, they're really interesting problems just because it really depends, it really requires you to think about the geometry of it. I think I did one of these problems in one of the videos that I made. Not mistaken. Yeah, let me try this one for you guys. So we have this integral. I have the integral from 0 to 1. You guys can't see this at the moment. Just give me a second. Integral from y to 1. Integral from 0 to y of f of x, y, z, d, z, dx, dy. Okay. If I have this integral, right here, let me move this over. Shift the screen a little bit. I have this integral right here where I have, you know, from 0 to 1, 0 to y to 1, and 0 to y. And my goal is to try to convert this to a lot of different types of integrals. This kind of the question you were asking? Really good?
Yeah, that's what I'm thinking of.
Okay. So when I'm thinking about these types of integrals, you know, the first thing you always want to do is try to draw this out as best as possible. It might be very difficult to, but we can at least try to do it as best as we can. And again, I am not an artist at all, and it's just kind of, you have to kind of think about this geometrically. So let's first write out our inequalities. I have here that z goes from 0 to y. I have that x here goes from y to 1. And I have that y goes from 0 to 1. Okay. Now, if I want to start to convert this to all different types of integrals, right? I have 6 different types. You know, I have dz, dx, dy. The next easiest thing I would think off the bat here would be to do, you know, dz, dy, dx, right? Because I already have the z up first. So I might as well just kind of convert down here. So how do I go about doing that? Well, what is this region right here, right? This is the projection. This thing right here is the projection onto the xy plane, right? And so I can draw this out specifically, right? I can draw this out. I could say that x is equal to y and x is equal to 1. So let's kind of draw these guys. Something like this. Now, if I draw x is equal to y and x is equal to 1, x is equal to y is something like this. X is equal to 1 is something like here. And y is from between 0 and 1. Now, I see that x, if I go in the x direction like this, I have to enter from x equal to y. I have to enter from this line and exit from x equal to 1. So I'm going to be in this region right here. This is my region that I'm worried about. So if I want to convert this to a dy dx, what I do is I now go vertically. I go this way, go in this direction. And where do I always enter from? Well, if in this region, I draw my lines going vertically, and I always enter the region from the line y equal to 0, right? I always enter this region going from this line. So my lower bound for y will be 0. My upper bound, I always exit from the line y equals x. So this one would have to be above, it would be bounded above by y equal to x, or be bounded above by x specifically. So y is between 0 and x. And then when I come up with my x bound, you know, I just come up with the lowest and highest numbers. I know this intersection point here is 1, 1, because I know that, you know, I'm bounded above by x equal to 1. So I'm bounded in this direction. So therefore, I'm between 0 and 1. So another bound could theoretically be this guy, right? This is the way I could do it. dz, dy, dx in that way. Now, what's kind of cool, at least in this part right here, is if I look at these inequalities, at least these first inequalities here, I could find actually all of my projections already, which is kind of interesting. Because what I can see here is I know that every single one of these variables, z, x, and y, are already only, in between, really, they're only in between variables of one other variable, right? They're not, dependent on x and y or something like that. But we can try to draw this fully out if you would like still. We'll kind of do this if we can draw this full thing out. So we can convert to another integral, x, y, z. The first thing I want to draw is that I want to say that z is equal to y. Right? What does the plane z equal to y look like? Well, I know the line z equal to y kind of looks like this. And, oh no. Theory, I did not want that. Sorry. So this is a line z equal to y, and we know it's going to be a plane that kind of goes in this direction, right? It's going to just cut in this direction. Something like that. So I also see that z equal to 0 is the bottom. So you can kind of imagine that I'm always, in this case, I'm always entering from z equal to 0, that's the xy plane almost, and I'm exiting through the plane here like that. I also can draw out this region. I know this region, what this region looks like on the xy plane now, right? I know that this region kind of looks like this, like that, kind of like that triangle. If I can maybe draw this a little bit better, kind of like this. And so I can kind of see that if I come and I kind of have this intersection right here, I would kind of get something that looks like this. I would kind of get this kind of plane that kind of gets cut off like that. It would kind of like this be this triangular thing that kind of, this plane and this kind of, this object which is intersecting with this plane, kind of coming across, this flat object coming across and kind of slicing it. And then from there, rising, as we get closer to this point right here specifically. So that's kind of at least the idea of that. Now, do you need to actually draw this? It's actually not necessary, and I'll show you why, but at least helps us out kind of visualize everything as much as possible. So what I want to do instead now is try to come up with a way, let's do something else, right? I now have this integral, let's go with respect to y first, okay? I want to go with dy first. I want to think about where I enter and exit this region from, okay? So where do I always enter and exit this? Well, what I need to do is I need to go in the positive y direction, going in this direction right here. And if you note, if I enter this region, right, this region is bounded by, right, this guy right here. This is my full region, right? I'm actually entering from the line y equals x. Right? I'm actually entering from that plane. I'm entering the region from that plane. Right? I enter that. So therefore, I can actually tell you that y below is actually bounded by x, right? Because I'm entering the region from x. So the plane y equals to x. And then I'm also leaving the plane. I'm leaving the plane. Oh, I'm drawing this the wrong way. I am so sorry. I'm very bad. Please yell at me. Sorry, everybody. I was doing x first. It's a good mistake to make. Sorry. We're going in the positive y direction. I'm going in this direction here. Right? The positive y direction is in this way. I'm so sorry about that. So I'm going in the positive y direction here. If I'm entering, I'm actually always entering still here from this plane. I'm actually entering from this plane. If you notice, I'm actually entering from the plane here, and I'm exiting from that line. So I'm actually entering from the plane that's kind of coming down like this, the z equal to y plane. I'm actually entering from there. So if that makes sense, I will need to enter from the plane z equal to y, which means that I need to be bounded below by z. And then I'm bounded above, actually, by this line, right? I'm bounded by this plane that's kind of cutting off like in this direction. So if I'm bounded by that, I'm actually bounded above by y equals x. So therefore, I'm bounded above by x. And so because of this, I just want to kind of point this out really quickly. When you're coming up with bounds for z, x, y, at least first, you want to be drawing your arrows going in the positive direction of whatever variable you're going in. I was making a mistake there. I was doing x first, so I apologize for that. But here, what I'm doing is I'm going in a positive y direction. I want to see where I'm entering from. I'm actually entering from that plane. I'm exiting from that line that's coming through it. That's kind of where this is coming from. And now what I do, because I have already integrated out y, I'm now going to project it onto the xz plane. And if you note here, if I project this onto the xz plane, it actually looks like this triangle, kind of going like that. So if I project this here on the xz plane, it actually looks very, very similar to the one we just did. Now, why do I know that? Right? Why do I know that this is actually the projection here? Well, what you can kind of imagine is that this projection is actually the intersection of these two planes coming together. I have the plane y equal to x that's cutting this off. I have the plane z equal to y, and the intersection of these two planes are what's getting projected, because y is independent there. I'm just kind of getting rid of y now. The intersection of that projected onto the xz plane. That's actually what the picture is. And so here, if I see this projection now is bounded. This above here, this line is z equal to x. And we can kind of see that because the intersection of y equal to z and y equal to x is just z equal to x, right? Because that's just you know, if if a is equal to b, b is equal to c, then a is equal to c in that same way. And so we can come up with our bounds for this very, very quickly in the same exact way that we just did over there. So the first way, if I think about this as, you know, if I go first, let's say dz, then dx. If I go z first, I draw my lines vertically, kind of like this. I draw my lines vertically. And if I draw my lines vertically, I'm always entering through 0, and I'm exiting through the line y z equal to x. And then for x here, I'm just going from my lowest to highest bounds, which is from 0 to 1. Or I could go, if I wanted to, you know, I could do dx dz and integrate with respect to x first. And you probably note that this is going to look very, very similar to how I just did this guy, right? Because it's the same exact triangle, which is nice. So I'm entering, if I draw lines going this way, right? I'm entering from the line x equal to z. So below, I would be bounded by z. Above, I'd be bounded by 1, because that's where I exit from. This exact line is x equals to 1, so that's where I exit from. And then lastly, my z would be bounded by 0 to 1. So this again could be dy dz dx, dy dx dz. And lastly here, I can come up here now and try to come up with the projection onto the xz plane, on the yz plane, right? I want to integrate out dx first. I'm now going to make a type 2 region of integration. And this was the way I was writing it before, so I apologize. I'm now going to go in this direction, which is in the positive x direction. And if I go in the positive x direction, the first thing I hit is the y, right? It's the x equal to y, it's that line. It's strictly this line right here. And it's that plane that kind of comes up. So we always enter from there. So I would be bounded below by y, and I exit from from this plane that kind of comes up like this, which is x is equal to 1. So I'm bounded above by that. And then I come through and I go, okay, I've integrated out x. I'm now going to project this onto the yz plane, right? I've integrated out x, I project this onto the yz plane. And we've already kind of looked at this projection because I know what this line is. This line is equal to y. And lo and behold again, the same dang triangle. The same dang triangle, if I have my yz plane. And again, from here, I can come up with my bounds in dy dz land and dz dy land. I think I'm going to stop there because it's the same exact idea, but I hope you get that point from there. So this is the same exact triangle. We can do it again. So the goals here, a lot of times when you want to think about this, is going to come a lot with projections. You can do a lot of these things, you know, drawing it out as best as you can. we can also start to look at what you have over here and come up with possibly some ideas. At least here, you might be able to think about this off the bat. You know, if I come up with x here, the dx command would also be pretty quick to do because I already have this inequality, which is the same inequality that I just came up with. Right, so it's the same exact thing. So sometimes you might be able to just flip this around and just exchange some things and get your answer. But the projections here are pretty important. A lot of the problems otherwise, if you didn't have a picture already drawn out, that would be very difficult for you to do that. Usually a lot of these problems that you would be asked, if you were asked to do this, I doubt you'd be asked to draw like something like this and kind of do this all out. But I wouldn't be surprised if they asked you to, you know, if they give you this what the solid looks like already, if they draw out the region and then maybe do that. But again, the goal here is again, we're going to be thinking about projection and maybe thinking about, you know, what does it actually look like? One technique is thinking about what the intersection of these two planes looks like, or the two surfaces looks like, or something along the lines of that. And coming here and playing like that too. That's it. Does that make sense? Whoever asked that question, I'm sorry. Was that Michaela that asked the question?
Yeah, it did. Thank you.
Yeah, no problem. Does anybody else have any questions about this specifically?
Yeah, just a quick question. What's the difference between like dz dx or dx dz for this problem?
You mean down here?
Yeah.
Or just in general?
Or yeah, either way.
What the difference is just being that I'm integrating. You know, if I go from dz dx, that means that I'm integrating with respect to z and then x. So what that means, at least here, if I project it, I want to be thinking about, you know, where am I going vertically because I'm projecting it that way. So if I think about dz dx or dx dz, it's just telling me which way I want to integrate. Sometimes it's a lot easier to integrate in a certain way. So we have those options. But the general idea, though, in total, there's three different types of triple integrals. There's the dz one first, which is usually called a type 1. There's a dx first, where I'm integrating with respect to x first, which is a type 2. And then I come up with this dy here with the type 3. Other than that, you know, flipping around the other limits of integration, dy dx or dx dz here or dy dz over here, is just kind of thinking about what the easiest way to integrate the region that's being projected onto the plane that we're worried about. There's not really a big difference between them unless there's a significant advantage for integrating something like that. Does that answer your question?
Yeah, that's perfect.
Yeah?
Thank
okay.
you.
No problem. Any other questions here? Okay, so what other questions could I answer then?
Could I ask a question about it's an integration problem I had for it was from the 15.1 WebAssign. And
Sure. What was it?
It was the you want me to say the problem, or do you want
that would be great if you could. Yeah.
All right, it was the double integration of the rectangle 9x sine x plus y, and then it had the first bound was 0 to pi over 6, and then the second was 0 to pi over 3. And my question comes from the second. So when if you were to integrate with dy and then dx, when actually doing the dx integration, it the like explanation video had you do it goes to cosine, and then you'd have to do a whole nother integration. And I was just confused why that was.
So is this the integral you're worried about? 9 times x times sine of x plus y?
Yes, that's it.
Okay. Something like this. Okay, so I guess a couple things here then. If I'm trying to come up with this integral and think about what the best way of integration is going to be, you know, I see a couple important things to note here. Firstly, I have a rectangle. So I know this is with respect to x, and I know this is with respect to y. So I know that I have something like some region of integration from pi over 6, and this is pi over 3. So I have this rectangle here. A couple of really, really important things to note about rectangles, right? I'm allowed to just flip the limits of integration, you know, however I want to. I can integrate this with respect to, you know, whatever integral I want. I could do this with dx dy or dy dx, whichever one I want, without really, you know, really thinking about it too much, because of Fubini's theorem. So I note here, at least initially, that if I integrate with respect to y first, it's not going to be too bad, because I know that whenever I integrate with respect to y, right? I'm going to be thinking about this as a constant. X is a constant, and I only have one function of that. I then integrate with respect to x first. I have a function here of I have some function of x times another function of x. That's a transcendental function. So I can kind of think about, I might want to use integration by parts here later. There's not really going to be a benefit to doing one or the other first. So I'm going to integrate with respect to y just so I can worry about that later. So what I'm going to do is I'm going to set this integral up. It's going to be from 0. I'm going to go from y first just because I can. I'm going to go 0 to pi over 6 of 9. Was that?
Okay, I see. From how you just explained, I see what the problem is. So they just didn't explain the fact that you had to use integration by parts. So okay, I see. So
so you would have to you would have to do integration by parts here. If I'm going to do with x first, right? I would usually have this would be u and this would be my dv because I want to get rid of it, right? That's pretty much what you would do. Yeah.
okay. All right, that kind of answers my my question.
Okay. Does anybody else want me to show you to go through that entire problem? I can go through that problem if anybody else wants me to. I'd be happy to. Okay. Well, then I will stop there then. Are you okay with it if I stop there then, Owen?
Yeah, I that answers my question.
Okay.
Thank you.
Cool. No problem. Okay. Any other questions that I can answer in general? Or specific questions?
On DJ's mini practice exam number 2, could you go over the third one?
Yes. Yes. You know, it's actually really funny. DJ and I put the same exact problem. We put the same exact problem on both of our exam worksheets, which is really funny. Okay, I didn't realize that. So I honestly really like this problem. I like these types of problems. I taught this course over the winter, and I think I had something very similar to this on my final, on this exam. I find this to be really good, this idea. I'm not too sure about anything else, but what DJ's feelings on this are. I get no say in this exam now, but it's okay. They shouldn't. Yeah. Okay. So I'm integrating this guy right here. This is the question you worry about, right? This guy?
Yeah, that's the one.
Okay. It looks nasty off the bat. It does. Okay. So if I asked you to evaluate this integral, the first thing you want to start to think about is, okay, a couple things. First off, do I even want to try to evaluate this right now? No, I don't even want to touch this as is. And why is that? Because if I was to integrate this with respect to z, I would have to use a trig sub off the bat. And the more I can avoid trig sub, the better. It's just my opinion. So we also see here some hints as to maybe what we want to try to use, or what integral or what kind of coordinate system we want to change it to, or maybe flip everything. The first thing I see here is this integrand. You know, sometimes it's not really important to look at the integrand to kind of give you a hint, but the integrand here is an x squared, y squared, and z squared, a plus. And I know if I go to spherical coordinates, this would eventually get changed to rho squared. So I would have rho squared to the 3/2, which would be rho to the 3rd, which is not bad, right? Then it becomes a lot simpler. So that begs the question then, you know, can I convert this, right? If I converted this to polar, cylindrical, probably wouldn't clear up a lot. So hopefully this would be the point to maybe, you know, go to, the goal is probably to convert this to spherical coordinates. So in order to do that, we have to kind of draw out this region. There's not really a nice way to kind of look at it other than to draw it out and to kind of think about it that way. So let's do that. Here, this first part means that z is between negative square root of 4 minus x squared minus y squared. This top part would be 4 minus x squared minus y squared. Then I would go from y here. I would go from 0 to the square root of 4 minus x squared. and x would be between 0 and 2. Okay, so there's a lot of things to kind of tackle here, and let's kind of go slowly. The first thing I want to think about, at least in my opinion, is to come up with a projection. So it says I'm on the xy plane here. Let's think about what this looks like just in general on the xy plane. So if I come up with this, I can actually see that the upper bound here is kind of going to be like a circular thing. So it's going to look like y squared is equal to 4 minus x squared, or x squared plus y squared is equal to 4. So I would actually get a circle of radius 2 on my xy plane. And if I do this, I note that if I draw this out, I'm going to be bounded below by y equal to 0. So I shouldn't have anything below y equal to 0. I should always just be bounded above by that. And then secondly here, x is between 0 and 2. So I'm bounded by this line right here and this line. So this must be my region on the xy plane. This guy right here. So if I see this, my theta component is already done that, because my projection onto the xy plane, when I come up with this, will be pretty quick if I start to think about maybe using the theta component too. Because my theta sweep is going to be from 0 to pi over 2, going off in that direction, right? Okay, but the first thing I need to do, I guess the next thing I want to do is think about what does this actually mean? Or what does that actually mean? So if I equate both sides, or I can do z equals that and z equals that, and take the squares of both sides, you would find that you would get z squared is equal to 4 minus x squared minus y squared, or that I would get x squared plus y squared plus z squared is equal to 4, which is a sphere, which means that I have both hemispheres, because I am below and above, like z is going through, right? Z is going through both here and through the top, right? So I'm going from below and above. And so because of this, right, if I do this now, I'm going to draw this out as best as I can. I have a sphere of radius 2, and of radius 2. As well, I know that I need to be just in this first quadrant. Well, I'm going to be here. That's really the only place I'm going to be. But I have a full z sweep. But that's what that means. I have this full z component here. So what's actually happening is, I'm going to draw this as best as I can. Again. So I would be only in really this first part up here, but I know that I have to be going down too. I will have to have the full sphere. So what's happening is I'm only going to be in this first quadrant of xy, but I'm going to be in both the z octave. I'm going to be in both of these guys. I'm going to be able to come down here as best as I can, kind of like this. So I'm going to have a full quarter sphere. I have basically taken just a quarter of this entire sphere and plucked it out, and that's what it is. And I get that from utilizing this. I know that I'm going to have to go all the way when I enter the region, right? When I enter the region, right, I must enter and exit from the sphere itself. So I need both parts. This part now tells me exactly which octave I really need to be in, how to orient that. So it's a little bit different, but that's what it kind of looks like. Now, I think the first thing to do when I come up, like we see we're in a sphere now, and I see that I probably want to use spherical coordinates because I'm on part of a sphere. So in order to do that, we come up with rho. Rho here I think is pretty quick, as it usually is. I start off at 0, and I exit the region. And I'm always exiting the region from the sphere of radius 2. So I always enter the region at 0, in this case, because my region starts at 0. And then I exit through 2. I'm always exiting from that part. I'm always exiting from the end part here, right? This is a radius of 2. So this would become rho squared equal to 4, and then rho is equal to 2. My theta component, well, I've already got my theta component kind of down. It's over here, right? My theta component, again, what I do is I project onto the xy plane. If I project this onto the xy plane, I get something like this. I get this quarter circle. And I see that I am going to be between 0 and pi over 2. Right? I would be between 0 and pi over 2. And the last thing I need, and again, one of the weirder ones, right, is this phi component. Now, what I'm going to do is here, I'm going to project either onto the XZ or the YZ plane. If I project onto the let's say on the YZ plane, kind of imagine I will smush this against that wall. Right, smush it against this wall right here. That kind of pushes it there. And if I project this onto the YZ plane, I'm actually going to get this full circle. No, sorry, this full half circle. Something like that. If I project that on there, because again, why do I need this? Right, I have to go below and above, and I'm fully in this direction, right? I have to go fully down here. And I can't have y has to be greater than 0, so I'm going to be in this direction. And so, if I come up with my phi, I see that phi is equal to 0 is up here, phi equal to pi over 2 is over here, and phi equal to pi is here. So I'm coming up in this direction. I start at phi equal to 0, and I start to move down. I see that I get this full theta phi sweep. I go from the full sphere. I have the full sphere basically here in terms of phi. So I'll be between 0 to pi over 2 to pi. And because of that, we actually get everything above and below the xy plane. And so therefore, we will have then that phi would be between 0 and pi. And these are my limits of integration because of that. And so what happens now is we then take this integral, and what we can do is we can set this up now. What I'm going to do is I'm going to take this entire thing here. This now becomes a rho squared, this guy. And so a rho squared to the 3 halves would then be rho to the 3rd, right? It would be rho to the 3rd to the 3 halves. And so this would be rho to the 3rd, and then I have to make sure I add the rho squared sine of phi. But again, I can integrate this in any way I would like, because again, this is all constants, which is really nice. So I integrate this 0 to 2, 0 to pi over 2, and 0 to pi. I would have a rho to the 3rd times rho squared sine of phi, d rho, d theta, dc. And from here, what I could do if I wanted to integrate this, but I could actually separate this out, use the fact that they're separable functions. This is usually a very, very cool thing to do when I'm doing spherical coordinates, because a lot of times this actually does happen. And I could integrate this out. I know that if I'm going to go with my phi component, I only have a sine of phi. If I have my theta component, I have no theta component. So it'll just be a 1, basically. And lastly here, I would have my rho component, which is rho to the 3rd, rho squared, which is rho to the 5th, d rho. And from there, you can integrate this and kind of get your answer. And if I'm looking at this, yeah, you're going to get something like that. At this point, right, it's just integration here. I think you'd get probably like a 2 here, you'd get a pi over 2, and then you get a 2 to the 6th, which is 64 over 2, so you get a 32. Probably something like that. 32, so you get like a 32 pi. Maybe that's your answer. Maybe something over 3, over 6. Oh, right, you would have to do this over 6 too. But yeah, you get the point. That's kind of how you would go about doing this here. Yeah, does that answer your question? Does that make sense, that process?
Yeah, that makes sense.
Cool. Does anybody have any questions about that process here at all that I could talk about?
I just have a quick question. This isn't directly related to this specific problem, but all of the problems we've done with spherical coordinates have had constants as all of the bounds. When would we ever be given a problem where they weren't constants, do you think?
That's a pretty difficult one. The only one that you would not, the only one that I could see where they would go and they might not give you constants. I think that's above our pay grade at the moment. I have never seen a problem on a midterm or anything like that without them being constant.
Okay.
Period. That does not mean that they won't have one, but I don't think you've ever, if it's not in the web assignment, which I don't think it was, I don't think any problems like that have shown up when you've done any practice. That would be very, very, very difficult, honestly. There are problems in the textbook that do that. The only thing that I could think of that would be dependent would be the row component. You might not have row starting at 0, you might have, if I have two concentric spheres and I want to find the area in between them, you might have like rho between 1 and 2, for instance, or something like that. But I mean, it would surprise the heck out of me if they did that. Yeah, because they really haven't tackled that at all.
Okay, thank you.
Yeah, no problem. All right, any other questions that I can answer? You have to think that a lot of these, because again, you know, you have 40 minutes, right? Or 35, 40 minutes, however long it's going to be. They can ask a lot of hard questions. I mean, hard questions, what I mean by hard, long questions, right? They can ask a lot of those. So you're not going to be asked to do a lot of full integration. Maybe one problem, that you should definitely be expected to at least integrate one thing. More than that is a lot, probably, it has to be very easy at that point. Because they take a lot of time. Setting up the bounds, though, is very, very reasonable to ask a couple questions on. What other questions could I answer?
I have one. So on the quiz this past week on Tuesday, number 2 was something about switching the integrals. Could we either go over that one or something similar to it?
Yeah, we can go over a change of integrals. Yeah, sure. Yeah, let's do that. See if I have a change of integral one. Sanjay, I see your question. We will do that next. So something like this. You think about something like, yeah, looks fun. So like asking something like this integral that we have right here and asking to flip the bounds, something like that. Here's the order of integration.
Yeah.
Okay, so let's do that. I picked a fun one, so this at least gives us some options. Okay, so I am so the goal of this always, and you always want to be very careful. You should never, under any circumstance, do this. If you do this, you will automatically, and I'm not joking, you will automatically get 0 points. Period. Because you cannot do this, and the reason why, right, is because this is dependent on x. Right? These limits are dependent on variables now, and we cannot go ahead and you know, change variables, change limits of integration like that if this is there. We only can do that via Fubini's theorem. To be able to change limits of integration, we need to look at the geometry of the problem and then come with an idea and think about like what idea and what way can I look at the geometry of my region in a different light. So please never do this. I should not even write it. Sorry, I shouldn't even write this to give you guys ideas. But please don't, because I actually saw a couple of on the last quiz when I was grading that, I saw a couple of students doing that. So make sure that you don't go ahead and do that. It's a very important concept there. The only way you can do that is to have a rectangle. We don't have a rectangle here. So the first thing you want to do is kind of draw out and make sure we have our limits. So we have this, and we have x from 1 to 2. 1 to 2, sorry. Okay, so let's draw this out. The first thing I want to do is draw out both of these functions. This is at least the technique. You draw out y equal to 0 and y is equal to the natural log of x. To do that, let's do this guy, xy. The first one will be y equal to 0, which is this line right here. And then I also have the natural log of x, which kind of comes in like that and goes off in that direction. I know that this point right here is at 1, right? The intersection point of this is 1 because I know the natural log of 1 is 0. That's how I kind of get that. This is at 1. And then we have that x is equal to 2. So we would have this region right here. And the reason why is I'm saying that y is between, I'm entering the region from this way, right? This is saying that I'm entering the region from this direction. I'm entering from y equal to 0, and I leave the region from y equal to the natural log of x. Now, my goal here is instead of drawing vertical arrows, I now draw horizontal arrows. So drawing lines like this. Okay, I now draw lines like that. So where do I always enter the region from? Well, I always enter from this blue line. Wherever I draw this line, I'm always entering from the blue line. And this blue line here is y is equal to the natural log of x. But when I come up with my region, my changing of region, and my change of, changing of integration here, I need to go ahead and think about, okay, well, I need x in terms of, I need x in terms of y. I actually need a function x equals something. And this doesn't give me that. So how do I change this? Well, I have y is equal to the natural log of x. The way to switch this around is to exponentiate both sides, right? That's the inverse part of the natural log. And so if I do this, this means that x is equal to e to the y. And this is my equation for this line. That's what this equation for this line is. And so we see that I enter from e to the y. I enter from this line e to the y. And I exit from the line x equal 2. Right? I'm always exiting from this line. I always exit from this red line here. So I enter through e to the y. And I exit from 2. Something like that. Now I just come up with my y bounds. When I come up with my y bounds, I think about the lowest possible value and the highest possible value. The lowest possible value is 0, so we go with 0. The highest possible value, though, is this intersection point. So what number is that, right? What number is that? Well, this line was y equals the natural log of x. So that point right there is just equal to the natural log of 2. It's some number, but it's the natural log of 2. Because that's the intersection point between x is equal to 2 and y is equal to the natural log of x, right? That's just me plugging in 2 to that. And so because of that, y goes from the natural log of 2. And therefore, what this means is if I want to write this integral with respect to x first and then with respect to y, I will then need to write the double integral from e to the y 2 and 0 to the natural log of 2, f of x, y, dy, dx. Sorry, dx, dy. Dx, dy. And that is my answer. So kind of zooming out and kind of thinking about the big picture of this, technique is as follows. You draw out your region of integration. Kind of make sure you draw out the correct region of integration if you can. What I suggest doing is equating your inequalities and drawing both those lines and making sure that you have the correct region based off of that. And then you flip everything, right? You need, if I want to go to dx, then first I need two functions of y that are bounding it. And so I know that I was entering the region from this line, the natural log of x. I was entering the region here. I was exiting the region there. So I know that this one was dependent on x and y. So I needed to exchange it to get x equal to e to the y. And then from there, I could find this top part right here. This bottom and top part would get me y, which is just the natural log of 2. And therefore, that's my answer. So the changing of integration is actually a really interesting technique. I've seen that asked a lot on midterms in the past. I wouldn't expect anything different. I would expect probably one of these. I know there was one on your quiz, but they probably give a lot of different. They're probably going to give a lot of different chances here for people to kind of better themselves on that question. So make sure you know how to draw the domain. That's a big part, and then making sure you know how to kind of convert from there. Does that make sense?
Yeah, so I just want to clarify, this kind of went from like a type 1 to a type 2.
Correct, yes. We went from a type 1 to a type 2 region.
And how did we knew that it was started at type 1 because of y?
We have dy, then dx.
Okay.
I'm integrating with respect to y first and then x. That's a type 1.
Okay, thank you.
I want to get too stuck in the weeds with the integral types.
Mm-hmm.
You wouldn't be asked to do that. You want to be asked, like, identify if this is a type 1 or type 2. That's a little bit niche of a question. Just know that if I'm switching with integration, this just means I'm starting with y and then going to x. Now I want to integrate with respect to x first and then go to y.
Okay.
Yeah. In this case, you are right, though. We're going from a type 1 to a type 2. if you want that terminology. Any other questions here? Okay, those are asking a question for a problem setting up a triple integral question on the worksheet I actually handed out, which was section 15.6. That was with the paraboloid one. So the question asks if the volume bounded by the paraboloids x equals y squared plus z squared, and x is equal to 16 minus 3y squared minus z squared. The volume bounded by these two guys. So I'm not going to go through the full integration here. I'm just going to set it up because the full integral here is absolutely horrifyingly disgusting, as I found out when I was doing the problem out. But setting up the problem is actually really, really interesting still. So let's at least talk about it. Because bounded by two paraboloids is actually a really interesting kind of idea. So we see we have these two paraboloids. Y and z here. And now I want to find the volume bounded between them. So again, as a reminder what the equation for volume is, right? It's just the triple integral e dv with a 1 in my integral, right? With a 1 in my integrand here. So in order to do this, we want to draw this out as best as possible. We see that I have x is equal to y squared plus z squared. So this is a paraboloid going infinitely in the x direction, going infinitely in the x direction, and starting from 0, 0. And how do I know that? Because if I plug in y equals 0 and z equals 0, I get x equals 0. So I'm going to be starting here, and I go out in this direction. I would have something like this here. And then I have this equation, which is 16 minus 3y squared, which minus z squared, which is another paraboloid. It's not a circular paraboloid, which starts to get a little bit interesting. It's not a completely circular one, but it at least goes still in the negative x direction. And how do we know that? Because these two minus signs here, we start at 16 because y equals 0, z equals 0 gives me x equal to 16. So this is 16 right over here. And then we go in that direction, right? We go in this direction here. And you kind of see something like this. So as you can kind of see, I'm bounded in between these two. I'm kind of taking two cups and kind of putting them together. I'm trying to find, it kind of looks almost like a football in some way. I'm trying to find the volume bounded by these two things. And that's my region of integration that I'm trying to figure out. Now, when I'm coming up with this, the first thing you want to think about is, I didn't tell you, for instance, what type of, what coordinate system to use, something like that. But because of this, it's actually not too easy to think about, which coordinate system you want to use. So initially, as I always do here, unless it's obvious, try to always go with Cartesian and then move from that. So what I want to do, so what I want to do is I see here that, what is going to be easiest to integrate at first, x, y, or z? Well, if I integrate with respect to z first, and I draw lines going up in this direction here, it's actually not, it's going to be very, very tough for me to think about that, right? Because if I move in different places, I'm actually entering and exiting from the same exact surface. So it's really not easy for me to think about it that way, right? And I would have to change it because depending on where I am, the surface changes, right? If I'm over here, or over here, the surface does change. So z might not be the best way to go. And a similar thing, y might not be easiest either if I go in, in this direction here, across. Because again, I'm going and entering and exiting from the same exact surfaces wherever I move from. So the next natural choice, or the only other choice we have, is going to go in the x direction. So if I move in this direction, would you agree then I'm always entering from that purple paraboloid, right? I'm always entering from there, which that purple paraboloid is x equals y squared plus z squared, right? It's that first one that's opening up in the positive x direction, and then I'm always exiting from that red paraboloid, the one that's going in the negative x direction. So we can kind of see that if I bound x here, I can do this pretty well by bounding below by my paraboloid y squared plus z squared, and bounding above by 16 minus 3y squared minus z squared. Something like that. So what you want to think about there is here we kind of went through the process of, okay, it's probably going to be best to go for x here because it's easiest to think about. I'm bounded by them and I can have a clear entrance and exit, strategy, and which functions are going in and going out. Now, once I integrate out x, what I do is I project this onto the YZ plane. And if I project this onto the YZ plane, what is this going to look like? It's kind of tough to tell. It's very difficult to tell. But one thing you might say to yourself is, okay, well, if I look at it from the x axis, if I do my viewpoint thing as we do in the lab, and I think this is a really cool thing to think about in the lab, right? That we kind of view it from the x-axis. If I take binoculars and I look at it from the x-axis here, right? I see the projection. If I see the projection, you've got to imagine if I see the projection of a football, if I look at it from the head of the football, it's going to just be that ovular shape, right? And now what is that? Well, it's actually, I hope you'd agree, it's actually the intersection of both of these paraboloids. That's going to be the biggest part that will be projected onto here. So this is actually a really interesting technique, right? To be able to find your projection, to be able to find your bound. One thing you would do after you integrate out one of the techniques, if it's not obvious, is to come up with the intersection of both of them, because that usually will become the projection onto there. So when I think about the intersection here, what does this intersection look like? Well, you can probably see that it probably looks a little bit like weird shaped because this is a little bit, flatter in some way. And if you don't know what it looks like, it's totally okay. But how would you figure that out? It's the intersection of this and that. And so what I want to do is equate both of them. So I get y squared plus z squared is equal to 16 minus 3y squared minus z squared. Something like this. So I'm going to get it to something that I know that maybe looks like an ellipsoid here, which I think it's going to start to look like an ellipse. I would do 4y squared plus 2z squared is equal to 16. If I divide all sides here, I would get 2y squared plus z squared is equals to 8. And this is the equation of the surface here, whatever this is. Now, a couple of things you can start to look at here. One thing is, okay, what are my axes? Like what's going to happen on my axes, right? If y is equal to 0, then z squared is equal to 8. And so z is equal to plus or minus the square root of 8, which is also like 2 root 2 some way. So z is going to be, 2 root 2 here, and also down here, negative root 8. And then if z is equal to 0, what happens there? Well, that's 2y squared is equal to 8, or y squared is equal to 4. So y is equal to plus or minus 2. So it's a little bit more inward. I want to make this a little bit more pronounced. And so we would get something that looks like this. Something like that. And this is my region of integration. Now you may say to yourself, is this polar region? Is this kind of a polar region? I wouldn't use a polar region because it's not really a circular region. It's an ovular region. It's an ellipse, which is not really well done by polar coordinates here. So to come up with my limits of integration here, you want to just go back to the bare basics of how do I come up with a type 1 or type 2 region. And so again, what we're going to do is we're going to think about this as a type 1 or type 2 region. It kind of what do I want to integrate first, dx, or dz, or dy? I'm going to go dz first. Doesn't really matter here. I'm going to go with dz first though. It looks a little bit easier. So I'm going to use a different color. In this case, I'm going in this direction. I'm going with dz first. And if I note here, where do I always enter from? I always enter and exit from the same exact ellipse. I always enter from the bottom part, I exit from the top part. And how do we write that in Cartesian, right? What we usually do is I solve for z here, right? I'll get z squared is equal to 8 minus 2y squared. And therefore, z is equal to the square plus or minus the square root of 8 minus 2y squared. Something like that. I can't simplify that anymore, right? That's it. So what's nice here is I see that z enters from the bottom part, this negative part. It exits from this top part. And so one way you could write this is go, okay, well, I know that z then is bounded below by negative 8 minus 2y squared. It's bounded above by the square root of 8 minus 2y squared. Something like that. And then I just come up with my y integration. My y integration here is going to just be between negative 2 and 2, right? As I've kind of figured that out. If you did not do that beforehand, one way you could do that, again, is to say when z is equal to 0, right? When z is equal to 0, where's y? Y is between negative 2 and 2. So I have this guy right here. I have this one right here. This is my x bound. This is my z bound, and this is my y bound. And so therefore, because of that, we can then write our limits of integration here and say then that we would get that the volume of E here is equal to the triple integral. We need to do x first, which is between x squared plus z squared at 16 minus 3xy squared, y squared plus z squared, and 16 minus 3y squared minus z squared. We then have z here, where we're going to go negative square root of 8 minus 2y squared to the square root of 8 minus 2y squared. And then you go from negative 2 to 2. And we would do this from 1 dz, dx we did first. So with respect to x, then we did with respect to z, and then we did with respect to y. And this is how you would write that limit of integration for that. And then from there, you would just integrate. You actually have to use a trig sub here. Do not worry about doing that. The very, very big important part to remember here is to come up with these bounds. So how do we do that again? Couple techniques here. First thing to do is don't automatically assume you need to go to cylindrical or something else. Come up with some bounds off the bat that make just physical sense. And if you need to, convert to another coordinate system. We saw here that I came in from this first paraboloid. I always exited from this outside paraboloid. And then what we did is I integrated out with respect to x. I project onto the YZ plane. I project onto the YZ plane. I get this ovular region. And how do I know that? Because I found that this projection is actually just going to be the intersection between these two paraboloids. So if I actually compute the intersection of these, I actually get the equation 2y squared plus z squared is equal to 8, which then gives me, my region. And then from there, I just come up with my region of integration, my limits as I do for any, two-dimensional region, as I've done in 15.1 to 15.3, and go from there. Yeah, that's kind of the answer there. Does anyone have any questions about what I did there? Any questions about the process there? This is a pretty involved problem, especially because we haven't done a lot of stuff with this 3 here, these types of problems here. But this is the same exact process you would use for any type of paraboloid problem if I have 2 paraboloids coming together like that, kind of making it look like a football. Yeah, that's it. Any questions there?
Is this kind of question, given like the time frame that we have, is this like more than what we would be expected to do?
Coming up with the limits of integration here is a little bit of a lengthy problem. If they kind of, I think this is probably teetering on it, a lengthy problem. The way you can shorten this actually pretty quickly is if you made this instead of a 3, you made this just a regular a 1 here. That shortens this problem actually a lot, right? Because it's actually a lot more simple to kind of go for a circle. Because that would actually be specifically a circle. In that case, the intersection between these two. A circle of radius 2 square root of 2. So because of that, if that was there, then this problem would actually probably be a little bit simpler because you don't have to kind of worry about these things too much, and you actually know what the geometry looks like instead of kind of fudging the geometry. Yeah, I mean, this is a problem though. If you had changed it to that, I mean, that's not. I wouldn't put it past them to put something like that on there. I think they might want to make you step it out a little bit more, and they'll give you more points instead of just saying do this. They might actually go and step it out a little bit more to make it a longer problem. But or to kind of give you more chances at partial credit and stuff. But I don't think this is a far-reaching question. I don't think so. I think it's a very reasonable question for them to ask. It's just a matter of how they shorten it to make it reasonable. Yeah, the type of question is not unreasonable at all. Does that answer your question, Brandon?
Yeah, it does. Thank you.
Okay, no problem. I'm sorry that it's also just a weird time too, so I don't know how they're kind of handling all this, and all these midterms and all that are kind of changing too because of how at the different time periods. So it's kind of different. Usually this midterm 2 would be half chapter 14, half chapter 15, right? So I've never seen this long of a problem on there in a midterm before. I've never. Have I seen a type of problem like this before? Absolutely, I have. And the way they do it is just to make this kind of a little bit simpler for you and kind of already give you a head start as to where they want to go. Like say they could go, for instance, write this in cylindrical coordinates, and they could just go and they could already put you in the state of mind that they want you to, which makes it kind of simpler. That's how they kind of shorten these questions. All right. Any other questions for here or anywhere?
Yeah, just a quick question regarding what do you think is the most likely format for this mini exam?
What do you mean by format?
Like, is there going to be like any multiple choice, or is it all just going to be like written out responses?
Oh, they will never do multiple choice, I think. I mean, kind of like what they did on the last exam, last exam. I mean, that's not really multiple choice too much. That was kind of more geometrical things. There's not as much there to do here. I mean, there's a lot of geometric interpretation, sure. But I think more here, these problems are going to be, the geometric interpretation. So in the past, kind of give you at least some ideas of at least problems that I've seen in the past that are maybe a little bit off brand. You might not kind of think about it. What they've done in the past too with some of the problems, they kind of stepped them out a lot. What I mean by stepping out a lot is they will kind of go through each problem and really step it out, the question. Now, I don't think the current exam writers are about that. They're about kind of telling you a problem and letting you kind of handle, where to go. So it's a different kind of task. But one thing you might ask too, that you really might not think about is questions like, what is the differential in spherical coordinates? That's a question they've asked before. Just write that. Or write the cylindrical coordinate differential, or convert a cone to cylindrical coordinates, convert a cone to spherical coordinates, convert different objects to different coordinate systems. Stuff like that is a little bit more not about integration, but about just understanding the coordinate systems, which I think a lot of times they ask questions on. Because they want to see if you're actually thinking in that domain in some way. I don't see how they could do a lot of multiple choice questions or stuff like that. You should be just aware that don't be screwed by some pitfalls of like, if they ask a question of true false ask, like they ask a double integral can't be negative. Like yes it can. Right? A double integral can be negative. Absolutely it can. Like it's a net volume. Or for instance, don't get trapped in some true false questions where you just can't flip the orders of integration. Like you have to use Fubini's theorem, for instance, that stuff. They might ask questions about that. Stuff like, can you do this? Can you do that? Why or why not? That might be something that they can do. It's really tough for me to get in the minds of them because again, this has all been so crazy and different now, and I'm trying to wrap my brain around of how they just did the last mini exam and try to extrapolate a data point of 1 to another exam. So it's tough for me to do that, but I would think that maybe they would do some more true false ask things of, can you do this type of integration? Can you do this? Can you do that? Are you able to? And why? And explain. That would be some questions that they would ask. I think maybe. I don't think multiple choice would be. I think it would be kind of, can you do this or can you do that? Like true false ask questions and explaining why. That would be kind of the most different ones they would do. Other than that, they love, I mean, this part is so important about coming up with limits of integration. That's going to be the bulk of it. I know for a fact it will be. It always has been. Yeah, you'll be asked at least once to integrate something fully. Make sure you know how to integrate something fully. You'll be asked at least twice, maybe 3 times to come up with limits of integration for something. Interpreting your answer is a really important one. Always know that if I have a double integral, right, with a 1, or a double integral, a triple integral with a 1 in my, there's a volume and an area of that domain. Yeah, I think those are the main things. I don't think I'm answering your question very well, but again, it's just kind of a weird new way, and I'm trying to figure it out too of what they would kind of ask. But I would go with, if they were going to do anything off brand, probably true false questions on, can you do this type of integral, can you not? Can you do this type of like thing? Can you use Fubini's theorem here? Can you separate something like this? Can you do that and explain why? Yeah.
Alrighty, thank you.
No problem. I'm sorry that I can't answer that better.
No, it makes
I'm kind of out of the loop too, purposefully. Any other questions that I can answer? I have about 18 more minutes or so left. 20 minutes or so. So any questions I can kind of do, or anything you want me to talk about specifically? I could take out my trumpet and play.
I have a question.
Yes.
So over like just like of all the grading that you've done for this type of exam, what's something that you see like people repeatedly get wrong on chapter 15?
Yeah, that's a good question. Firstly, the thing that I told you about, the change of integration, that's a huge one where people just go and flip it. Like this one, they would just flip these two. That is something I've seen. I mean, every single time we have a question like that, 25% of the students do that. And we are told to give them a 0 for the entire question. That's a fact. That's something that I really have seen before. I think one thing as well that a lot of students get wrong, looking back on this, you know, a simple thing is just when you change integration, when you change the spherical, or you change the polar, or you change the cylindrical, making sure you include the r, making sure you include the d, you know, the rho squared times sine. A lot of students don't even know too that, right? A lot of times I've seen problems where they ask for the area of d, and it's just the double integral with a 1 there, right? Or the volume of a region E. It's just a triple integral over my region of 1 dv. These are things that students just don't know, and they're like, what do I put in for there, right? And a lot of times people just make up an integral, and you go, why did you come up with that part, right? Some people, I've had people like, you know, if they're integrating like the area of a circle or something like that over area of a circle, they'll put like x squared plus y squared in here, just cause. And you shouldn't do that, at least for there. That's at least what I've seen. I think another big thing to come up with that I've seen in the past. So there was a question I remember on the midterm last time. Was that the last time? Yeah, where you know, students didn't know what a differential was. They didn't know what the concept. We had to tell them like what is a differential? Like this is a differential, right? The dA here and the dV. These are differentials. And sometimes if you don't know that, right, that's saying a lot, at least about, you know, that idea of at least if you don't know what a differential is, that's a very tough question to answer because you're asking what the differential is. Kind of going back here, you know, being able to just integrate and that is, a lot of students still have trouble with just pure integration. Oh, one thing okay, this is actually one thing. I'm sorry, I'm remembering things slowly but surely. I'm sorry that I'm kind of scattered. This one is coming to me. If I have, a lot of times students will go like this. They're like we have like this triangle region. I'm making something up. Like this would not be that, this would be a really complicated triangle region, but just kind of bear with me. It would kind of go like that. And we would ask them something like, x plus y, dA. And like, let's say this was from like -2 to 1, and this down here was -1 to 5, let's say. Students will go off the bat and say, okay, well, it's -1 to 5, -2 to 1, x plus y, dx dy. This is a huge no-no. And like, why is that, right? If I have all constants here, it tells me I have a rectangle. I must have a rectangle. And so here I don't have a rectangle. This is not a rectangle. So if I have all constants in all 4 places, or if I have all constants in all 6 of these places, I have to have a box. I have to have a rectangle or something like that. So this is a big one, honestly, where students don't really understand that if I have something, I've seen students in the past not really understand that if I'm coming up with limits of integration for something that's not a rectangle, I cannot have all constants here. That's a huge, huge, huge issue that a lot of people see. Right here, you would have to make this either a type 1 or type 2, right? You have to go and say, oh, okay, well, it's probably going to be easier to go with a type, dx first. It's going to be a little bit easier to go dx first instead of dy because, for instance, dy here, if I do that, I enter from the same region, but I exit from 2 different ones. So it'll be easier if I go in this way, right? Because I'm entering from this line and exiting from this line. So this is a big one. I've seen it a lot. A lot of these questions, but students just come up with these and they go with the limits of integration and they come up with it and it's just all constant. And you go, it's not a rectangle. You can't do that. If it's a rectangle, great, but you can't do that either of that. So make sure of that. I mean, just I think the big thing also is that they're not going to ask a terribly hard question for if they do a spherical coordinate question or a cylindrical coordinate question. They're not going to ask really hard questions about. But knowing how to find your theta and know how to find your phi and all that, a projection is a really important thing that a lot of students don't get. But it's from like a more basic standpoint, the things I just kind of pointed out, those are the big ones that students I see all the time mess up. And thinking correctly, but it's a very natural thing to think. I get why people think of it. It's just the fact that you have to think about kind of the ramifications of what does it actually mean for x to be between -2 and 1 and y to be between -1 and 5. I have no restrictions. I have nothing else on that. So you have to have a box if you come to that. So those are the big things that I've seen. I'll keep thinking about it, but I think those are the big ones that I've seen in the past. That are at least easily easily fixable. I think they're easily fixable and easily being able to change that. Does that answer your question?
Yeah, it does. Thank you.
Yeah, no problem. Yeah, those are the biggest. Any other questions that I can answer?
Do you think they would give us like integration by parts problem or like use like the half angle, double angle theorem?
Integration by parts, yes.
Okay.
I think it's reasonable. Half angle, double angle formulas, probably stretching it a little bit. I wouldn't. I mean, again, it seems like the transition of these exams, sometimes they come up with some, different ones. I think just knowing like how to convert cosine squared or sine squared is probably not a bad thing. Cosine squared, you go 1 plus cosine 2 theta over 2. Sine squared would be 1 minus cosine squared, a cosine of 2 theta over 2. I think they wouldn't ask anything higher than that. If they ask a trig subformula, please just close your laptop. Because that's really brutal. They would never ask that. Integration by parts, though, yes. I think that's very reasonable. They're not going to ask a terribly hard one. But I know it sounds silly, but going back to the integration by parts one, maybe there's a way to avoid doing integration by parts by integrating something first. For instance, and let me just, because I think it's actually a really, really good question, at least to think about that. If I have something like this, I don't know. So something like that, right? I have a rectangle here, and x e to the xy. I hope you'd agree that if I was to integrate this first, would you agree that I would have to use integration by parts here, right? Because I have x times another function of x. So maybe I go, okay, well, what if I integrate with respect to y first instead? And you can do this, right? Because of Fubini's theorem, I have a rectangle, so I can do that. Just flip 1 to 2. And what's nice here is if I do this, the integral of e to the xy, I let x be a constant, so that's going to be 1 over x between 1 and 2 at dx. And so here, that's nice. And that eliminates the idea that you need to do integration by parts. So that's something that I've seen actually presented multiple times, where they present the integral in a way that makes it very, very difficult. You can do it, but it just becomes very difficult, sometimes impossible, actually, depending on which way they do it. And so you have to flip it. You have to remember the Fubini's theorem to flip it that way. I mean, you could integrate this with integration by parts. That's totally fine. Would you want to? No, I don't think so. At least here. So you can kind of get around that and skirt that. Yeah. So just be aware of that.
Okay.
So kind of the same. Yeah, yeah. Does that make sense? I'm sorry. I unfortunately don't know. I would not put it. I mean, I can't say no for sure. Integration by parts, though, yes. I wouldn't. I mean, that's something that could be expected. U sub, yes, like that.
Okay.
Trig sub, no. But converting cosine squared and sine squared, that's teetering on a difficult thing, but not uncommon. I've never seen that, honestly, in an exam. I've never seen them go from cosine squared to sine squared. I've seen integration by parts, though. Not frequently, but I've seen it. So I think that's very reasonable, too. They're not going to ask a really tough one, but if they do, just make sure you know how to do it.
Okay, thank you.
No problem. Yeah. Any other questions that I could answer? Oh, there was a chat. I'm sorry. Oh, yeah. Thank you. Yeah. So, I mean, I'll stick around for a little bit more here. Trying to think of anything else that I could think about here. You know, when you're doing this problem, when you're studying, you know, I do also have all those videos up on YouTube. Feel free to post this. I'll post this also on YouTube too. So hopefully that will be helpful for you to kind of go back and kind of see some things. I also have tomorrow too. So if you have any questions, you can come to that. But when we're doing these problems and you're coming through these problems, I hope you see that there's a reason why this course is called Analytic Geometry and Calculus. Because geometry is so important here. The geometric things all over are just so ingrained in us, especially in chapter 16 too. It doesn't seem like it now, but the geometry is so important. And it helps us visualize how to actually go from geometry to the actual analytical side. And noting that is a really, really big and important part. So do not at any circumstances shy away from the geometry. If you do, you will start to not gain an understanding and actually become worse off in being able to come up with more interesting problems and come up with problems that might seem a little bit far-fetched. Because if you understand how to look at something geometrically and draw it out, coming up with the bounds of integration, it's a difficult part, but if it's drawn out, it's a lot less difficult. And it's a lot less difficult if you're able to visualize the process that you're kind of going through it. So, you know, I am always overly cautious. I'm a very visual person. I always like to think about things visually. And the first time that I was taught Calc 3, when I was a freshman in college, This was my first legit math course when I was in college. I realized that I was scared to write too much, always. I was scared to put too much to my paper. I was scared to, that I wasn't able to visualize things properly. And the reason was because I was just too scared to try to visualize it. I was scared that I should have been looking at it from a different way where I didn't have to visualize things. I could just do things analytically. And immediately my professor, who was also my advisor at the time, said, no. You need to visualize these things as best as possible. You need to go ahead and draw these things. You need to go ahead and actually do this out because you're not going to be doing well otherwise. You won't do well otherwise. And it came to me that, in every class that I was doing, even differential equations or even higher level math courses, it is so important to me to be able to draw things out to do that because it makes the world make more sense. And the more you can make the world make more sense, the better equipped you would be for the world and also for exams and higher level problems. So yeah, don't be scared of the geometry. Geometry helps you out and formulates what we know about life. So don't be scared of that. Anybody else have any other questions, even small questions that I could answer? Are you all doing okay? I'm glad that those leads are helpful. I'm very happy to do them. I know that you guys, this class is a lot of information. So it's a lot. And so the least I could do is do this. And I'll put as much effort as I can to help you guys. So I'll stick around for a little bit more. I'll stop sharing my screen at the moment, but thank you guys for coming, at least here. I'll stick around though, if you have any other just general questions or anything you want to talk about. If you have any lab questions too, I'll be happy to answer them also. Talk about that.
Thank you.
Yeah, no problem.
Yeah, thanks, Nick.
Thank
No
you.
problem, Andrew. No problem, guys.